Yeah, good morning all. So to the continuation of the elimination reaction. So today we are going to discuss the orientation of the orientation in elimination reactions. So generally in the elimination reactions, the orientation means on which side the elimination is takes place. Okay, the elimination means where the two groups or the two atoms or one group or one atom is going to eliminate it from that particular compound here, right? So, for example, if more than so more than one side is a beta hydrogens are available, in that case, from which side is preferable for the elimination of the group or the atom here, right? So, to explain this particular orientation of the elimination reactions, so there is some rules. Okay, there is some rules are there. So, according to that rule, we will follow that particular elimination reactions here. Okay, so first we'll see the set job rule. Okay, yeah, the set job rule. So generally the set job rule, according to this set job rule, where the elimination reaction, the orientation in the elimination reaction is takes place towards the formation of the highly substituted olefin or the alkene here, right? So you can see in this particular example, yeah, right. So here, right? So this particular 2-methyl 2-chlorobutane is taken, right? 2-methyl 2-chlorobutane, where okay. So on this particular 2-methyl 2-chlorobutane, right? So there are two beta hydrogens are there, right? So this is beta hydrogen, and this is also beta hydrogen, right? There are and this is also beta hydrogen, right? But these two are same, right? Because the bonding connectivity is same, so these two methyl groups are same here. So this is one, this is two. There are two beta hydrogens are available. Okay, so in that case, on which side the elimination is preferable, right? So you will get the more means we'll get the both possible products here, but one product is obtained as major product and another is obtained as a minor product here. Okay, so here upon reaction of this particular 2-methyl 2-chlorobutane, right, with base the water here, the OH minus is going to abstract the proton here, right? So it abstract the proton from this, or it will abstract the proton from this here, because on both side it is possible. Okay, so in that case, right, so we are getting here the 2-methyl 2-butene and 2-methyl 1-butene, right? So this product 2-methyl 2-butene is obtained as 80% and this is obtained as 20%, where this is your major product here. Okay, and this is minor, right? So why this is major and why this is minor here? Okay, so when you see this, okay, so 2-methyl 2-butene, right? So it is tri-substituted with olefin, right? 1, 2, and 3, right? So there are tri-substituted. Okay, this is 1, this is 2, and here, yeah. So on either side of this olefinic bond, there are 3 methyl groups are attached here. That's why it is tri-substituted. And if you see this particular compound, right, the 2-methyl 1-butene, it is obtained as a 20%, means it is minor compound here, minor olefin, the minor product. Okay, so here 1 and 2, and on this carbon there is no substitution because both are hydrogens only, but we won't consider hydrogen as a substituent here. Okay, so it is disubstituted. So according to Shedjob rule, right? According to Shedjob rule, the more substituted olefin is the more stable, and the more substituted olefin is obtained as a major product here, right? So the orientation of olefin in this particular rule, Shedjob rule, is uh, okay, explains that the more substituted olefin is obtained as a major product, or the okay, it is preferable pathway or the route here. Okay. Yes. And the exemption, there is an exemption for this shade job rule here. So when the substituent, right, when the substrate molecule is attached with the bulky groups here, right, bulky groups, then means the particular beta hydrogen is, right, beta hydrogen containing carbon is attached with the bulky groups. In that case, the shade job rule is fails here, right? So you will get the opposite, means anti-shade job product here, right? Because the bulk is here, the steric hindrance, right? The steric interactions may orient, means may uh, operate this particular reaction here, right? So due to this steric hindrance, okay, so the the obtained product may not be stable. That's why this particular shade job rule is violated in case of bulky substituent on the beta hydrogen carrying carbon here. Okay, so in this example, you can observe. Okay, right. So here the 2 chloro 2 comma 4 comma 4 trimethyl pentane, right? So here you see this is the beta hydrogen here, right? So this is the beta hydrogen. Okay, so okay, this is the beta hydrogen. Sorry. Yeah, right. So here two products are obtained. Okay, so by the elimination of, right, so by the elimination of this hydrogen. Okay, so by the elimination of this hydrogen here, so we are getting this product, right? So by the elimination of this hydrogen, we are getting this product here, right? So there are two products like 2 comma 4 comma 4 trimethyl 1 pentene, right? And here is a 2 comma 4 comma 4 trimethyl 2 pentene. Okay, so we are getting this product is, right, where it is a di substituted, right? This is di substituted because one, two, there are two substitutions are there, di substituted, and this one is a tri substituted, right? Tri substituted here. So as per shade job rule, okay, as per shade job rule, the more substituted olefin is a major product, right? But in this case, right, in this case, the more substituted olefin is obtained as a minor product here, and the less substituted olefin is obtained. This is obtained as a major product here because of the steric hindrance, right? You see here this methyl, right? So it is facing some steric repulsion with this methyl group here, right? Here the tertiary butyl group is there. So tertiary butyl group, it is bulky substituent here. So due to having this steric hindrance group, bulkier group, right? So the product may not be stable. That's why you will get the anti-shade job product, right? So in the bulky substituent, right, the shade job rule is fails here. Yeah. So one more example you can see here, this one. Yeah. Next, so Hoffman rule, right? So one more rule explains the orientation of your elimination reaction, right? The orientation of the elimination reaction is a Hoffman rule. So Hoffman rule, generally it is applied for the quaternary ammonium salt, right? So the Hoffman rule is applicable for the quaternary ammonium salts here. Okay, so according to Hoffman rule here, right? So where this particular right? So a particular compound, the quaternary ammonium salts here, right? So you see where the beta hydrogens are eliminating, right? You see this is the beta hydrogen here. Right? This is beta. Right? Yeah. So this is your beta hydrogen, and in this side, this is the beta hydrogen here, right? So where the elimination of quaternary ammonium salt is takes place in this particular elimination reaction here, right? So due to shifting of, right? So due to shifting of this beta hydrogen towards this carbon, so where this quaternary ammonium salt is going to eliminate it, okay? And due to shifting of this beta hydrogen, where this is going to eliminate it here, right? So we are getting two products, right? We are getting these two products here. This is the ethylene, and this is 1-propene. Okay, and ethylene is obtained as a major product, and 1-propene is obtained as a minor product here, right? So this is reverse. The Hofmann rule is a reverse to your State-Jap rule here, right? So the less substituted olefin is the more stable here, right? The Hofmann rule. You can see the mechanism how this reaction is takes place, right? Here the base is obstructing this proton here, then this bond is shifting towards this carbon, then it leads to removal of your quaternary ammonium salt, and it is going to form your, okay, your olefin. Ethylene is a major product here, right? And another way of the mechanism is, right? So either this beta hydrogen or this beta hydrogen is going to eliminate it. If this beta hydrogen is going to eliminate it, then we are getting this particular, right? So shades of product, right? Shades of product, or we call this is anti-Hofmann product. Anti-Hofmann product, right? Here the shades of rule and Hofmann rule both are quite reverse here. In the Hofmann rule, more substituted olefin is more stable, and in the, right, in the State-Jap rule, the more substituted olefin is more stable, and in the Hofmann rule, the less substituted olefin is more stable here, right? So both are reverse reactions. Okay. Next, elimination versus substitution. This is very, very important in the exam point of view. This, right, this is very important here. Elimination versus substitution, right? So substitution. So when the reaction is takes place, right? So in the elimination reactions, okay. So with means the due to, right? So due to the nature of the substituent or the reactant or your what is it, the okay, the what is it, that particular sources here, right? So there is a competitive reaction will be takes place, right? There is a competitive reaction will be takes place here. That is a elimination and a substitution. And what are the factors, right? What are the factors favoring the elimination reactions, and what are the factors favoring the substitution reactions here? Okay. So when the particular reaction is takes place, right? So the first factor is the structure of the substrate molecule, right? The structure of the substrate molecule. So generally, if the substrate molecule, okay, if the substrate molecule is bulkier, right? If the substrate molecule is bulkier compound here, or the large compound, where it, okay, so the elimination reaction is favorable. And if the substrate molecule is less, okay, bulkier here, then the elimination is takes place here. Okay, next, the nature of the base. Okay, so the this particular substitution and the elimination is takes place according to the nature of the base also, right? So base means where the abstract the proton here, right? So yeah, so here the basicity, right? The basicity of various groups here. You can see hydroxy group and thioalcohol group here. Okay, and acetate group and chloride group and iodide group and the water. So this is a basicity order here, right? So due to presence of these groups also favored the substitution or the elimination here. Okay, so for example, if the OH minus group is there, okay, where the elimination is favored for this one, and if acetate group is there, the substitution, sorry, if the OH group is there, right, so it favored for the substitution, and if the bulkier base is there, right, means less basic here, so less basic group is there, so the substitution will take place here, right? So as per this order, you can right, you can predict the either substitution or the elimination, right? Next, the polarity of the solvent, right? So generally here the less polar solvents, okay, less polar solvent means generally if the water is there, so water is a more polar solvent here, right? And if the less polar solvent is there, so it promotes a bimolecular reaction by solvolysis here. Solvolysis means where the water is involving in this particular reaction. Okay, and generally this particular polarity of the solvent, right? The polarity, if the more polar solvent, it promotes the elimination reaction, right? The more polar solvent, it promotes the elimination, means it favors for the elimination reactions than the substitution reaction. Okay, and the effect of the temperature. The next factor which promotes, right? So the effect of temperature. So generally here, the higher temperatures, right? The higher temperatures is favored for the elimination reactions, and the lower temperature, right, promotes the substitution reaction here. Okay, so higher temperature promotes the elimination reaction, and lower temperature promotes the substitution reaction here. Okay, and the substituents on beta carbon. Generally, if the electron withdrawing group is present on the beta carbon, right? Yeah, right. So if the electron withdrawing group is present on the beta carbon, for example, here, okay. So this is your some X, the reference group is this is alpha here, this is beta. Okay, so beta hydrogen is here, right? So for example, this beta hydrogen, right? So beta carbon is carrying any, yeah, it is carrying any electron withdrawing groups like nitro, right, or the cyanide, okay, or carbonyl groups here, right? So then it favored for the elimination reaction because they are electron withdrawing groups here, right? So these presence of these groups here, presence of these groups on the beta carbon promotes the elimination reaction, right? If there is no planar carbons, right? If the carbon is planar, means without withdrawing groups, so it promotes the substitution reaction. Okay, so these are the some factors which promotes the elimination and the substitution reactions here, right? So this is your elimination reaction. Okay. So next here the pericyclic reactions. So pericyclic reactions very important. So in the pericyclic reactions, what are the pericyclic reactions? Pericyclic, right? The cyclic reactions. Okay. So where the right the products are the cyclic products here, right? And generally these pericyclic reactions are right unimolecular reactions or the bimolecular reactions here, and these are concentrated reactions, right? The first feature of this pericyclic reaction is these are the bimolecular reactions. Sorry, these are the concentrated reactions here. Okay, what is mean by concentrated reactions? So concentrated reaction means single step reactions. Okay, these are the single step reactions. No intermediate is formed, right? So these reactions proceeds by formation of the transition state. Okay, transition state, either 3-membered, 4-membered, 5-membered, or 6-membered transition state here, right? So we won't observe any intermediate state, right? Here we have two kinds of states here during the when a chemical reaction takes place here, right? Either that particular reaction proceeds by the formation of intermediate, or it may be proceeds by formation of the transition state. And those reactions which are proceeds by the intermediate, right? So they will be stepwise reaction here, non-concerted reactions. And those reactions which are proceeds by the formation of the transition state, these are the concerted reactions, single step reactions. These are the stepwise reactions. These are the single step reactions, right? Where the bond breaking and bond making takes place simultaneously here, right? But in the intermediate mediated reactions, you can first, okay, first the bond cleavage will be takes place. You will get the intermediate, then the bond making. Here the bond breaking first here, and after that the bond making will be takes place. But in the transition state mediated reactions, both processes, bond breaking and bond making, takes place simultaneously. Okay, so here all the pericyclic reactions are proceeds by the formation of the transition state here. Okay, and these pericyclic reactions are takes place in the presence of thermal or the photochemical conditions here, right? So they will carried out in the thermal conditions or the photochemical conditions, right? In the presence of delta, right? Delta means thermal, okay, or photochemical, H nu, right? Photochemical conditions. So both conditions are favored here. Okay, and the classification of pericyclic reactions. So generally, pericyclic reactions are classified into 5 types here. Okay, pericyclic reactions are classified into 5 types here. Those are electrocyclization reaction, cycloadation reaction, sigma-tropic reactions, okay, and ene reactions here, right? Yeah. So what are the electrocyclization reactions? So this classification is very important, right? The classification of the pericyclic reactions is very important. So very simple, where the electrocyclization reaction, right? The electrocyclization reaction means where the migration of the electrons, right? The migration of the electrons from one carbon to another carbon will be takes place. Okay, and these are the means either it is ring closure or the ring opening reactions. Both will be takes place in the electrocyclization reaction, right? Where the forward reaction is ring closure reaction here, and the backward reaction is a ring opening reaction. Okay, so you can see, right? So in this particular 1,3 diene, right? 1,3 diene here. So where the migration of the, right? The migration of the pi bond electrons, right? Migration of the pi bond, right? Here, the shifting of the pi bond. So where this pi bond is shifting here, right? It is going to shift on in between these two carbon, and this pi bond is closing the ring, and we are getting this cyclobutene, right? Cyclobutene. So one pi bond is consuming in this reaction, and it is giving the product cyclobutene here. Okay, this is electrocyclization, right? Electrocyclization means electrons are moving. Okay, electron are moving. This is your forward reaction, and the backward reaction where the ring opening, right? Where this you can see here, this migrates here, then this migrates here. Okay, then the ring opening will be takes place. Okay, so equilibrium reactions. All these are the equilibrium reactions. Okay, and one more example you can see here, the right hexa 1,3 triene here, right, where 3 pi bonds are there. In previous case only 2 pi bonds are there, and we are getting the cyclobutene, but here the migration of this pi bond, right? The sequential means in the conjugated system. Okay, in the conjugated system, the sequential migration of the pi bond will be takes place. This bond shifts here, this bond shifts here, and this pi bond is closing the ring. So we are getting this product cyclohexa 1,3 diene. Okay, so where by consuming of the one pi bond, okay, so we are getting one sigma bond here. Okay, so this bond, this pi bond is forming a sigma bond. Okay, so like that, where the electrocyclization reactions, and you see these are the unimolecular, right? Unimolecular electrocyclization reactions, because only one molecule is participating in the reaction, right? Only one molecule is participating in the reactions, and these are proceeds through the formation of transition state here, right? No intermediate is formed in this particular reaction, right? So here also, right, electrolysis means this pi bond is conjugated with this, right, carbocation positive charge here, where this pi bond is shifting here, and we are getting this cyclopropyl carbocation, right? Next, the cycloaddition, right? So electrocyclization reactions are unimolecular reaction where only the single molecule is participating in the reaction. Now the cycloaddition reaction, these are the bimolecular reaction here, right? Here the two partners are required, two partners are involving. Here the partner one here, okay, partner one, and here the partner two, right? Two partners are involving in the reaction here, like this. Okay, so this partner one here, this is partner two, where the cycloaddition, right? The cycloaddition reaction, where the addition is takes place. This pi bond comes out and attacks here. This is attacks here. So where we are getting this, again we are getting the cyclic product here, like cyclobutane derivative. Okay, and this is a forward reaction, and this reaction takes place under either thermal condition or the photochemical conditions. Both conditions are favorable here, right? So, and the backward reaction where the opening of this cyclobutane is takes place, right? The forward reaction where the formation of the cyclic product, and the backward reaction where involves the, again we will get your starting materials, your substrate molecules, again we are getting back here. Okay, so how this is takes place, you see this bond shifts here, okay, and this bond shifts here. So again your two partners are separated. These are the equilibrium reactions, right? So all the pericyclic reactions are equilibrium reactions here, where forward reaction as well as the backward reactions takes place with the equal rate here. Okay, and you see here this is the example for the 2,2 2+2 cycloaddition reaction, because here the 2 pi bonds are there, so 2 pi electrons are there, and here is 2 pi electrons are there. So It is 2+2 cycloaddition reactions, and we are getting the cyclic derivative here. Okay. Yeah, and one more example, right? So here the participating partners, they may not be the same, right? So you can proceed with the different partners here, right? Here in this particular example, you see a diene is taken, right? Here the two pi bonds are there, and here is only one double bond is there, right? So this is shift here, this bonds here, and it is shift here. So we are getting this cyclohexene derivative. So it comes under the 4+2 cycloaddition reactions, right? Because the partner one, right? Yeah, the P1 is with 4 pi electrons, and P2 is with 2 pi electrons here, right? So we are getting this particular cyclohexene derivative. And here also you can see, right? Yeah. Next type is a sigma-tropic reaction. Okay. So sigma-tropic reactions. Sigma-tropic reactions generally these are the rearrangement reactions. Okay. So the migration of the sigma bond, here. Okay. So in the previous cases, in the cycloaddition reactions and electrocyclization reactions, where the migration or the shifting of the pi bond is takes place here. But here in the sigma-tropic reactions, the migration of the sigma bond, right? The sigma bond through pi electrons here, or through pi system is called the sigma-tropic reactions. Okay. So here you see in this particular example, okay, so this R group is, right, the R group is migrating. Okay, so this R group is migrating here. Okay. Right, here the R group are hydrogen. So in this example, it is given the hydrogen, right? So the H1, it is migrating from C1 to C5. Okay, so previously the H1, right, it is attached on the C1 carbon here, and in the product you can observe it is on C5 carbon. Okay, so in previously it is C1, right, C1H1, here C5H1, right? So this H1 hydrogen is migrated, right? So here this shifts here, this shifts here. Okay, then this comes out here. Okay, so it is migrated through the pi electronic system, right? Yeah, so you will get here, right? So this is sigma-tropic shift, and depending on the positions where the migrating group is attached, right, depending on the final fate of the migrating group, it is classified into 1,3 sigma-tropic shift, 1,5 sigma-tropic shift, and 1,7 sigma-tropic shift, 3,3 sigma-tropic shift. So all these are different types of sigma-tropic shifts here, depending on the migrating group final attachment here. Yeah. So in this example, you can see. So yeah, right. So in this particular example, right, so where this sigma bond is, right, the sigma bond is shifting here, and it is right, so this sigma bond is shifting through this pi electronic system, and it is attached here. So 3,3, it is called as 3,3 sigma-tropic shift here. Okay, and in the next example, you can see this particular R group. Okay, so this R group is it is migrating from C1 to C5, C3. Okay, so this is 1,3 sigma tropic shift. Okay, so like that, we can have more examples here, right? And here also this aryl, okay, allyl phenyl ether here, aryl ethers, right? So aryl ethers where the 3,3 sigma tropic shift, right? So in this sigma tropic shift, right? So you have to give the numbering 1,1 number to the migrating, right? That's the migrating bond. Okay, so the which bond is going to migrate, right? So it gains a 1,1 numbering. Okay, so now you see, so it is going to attach here, and it is comes out here, and it is migrating here. So we are getting this product. This is the example for the sigma 3,3 sigma tropic shift here. Okay. Yeah. Next, the stereochemistry of the pericyclic reactions. Yes. So in the electrocyclization and cycloadation reactions, right? So the ring closure or the ring opening takes place by the migration of the pi electrons here, right? And this migration of the pi electrons, right, will be takes place either two rotations here, right? By two rotations. So if it is electrocyclization reactions, in the electrocyclization reactions, we will apply, right? So we will apply the either con rotation or the dis rotation. Okay. So con rotatory electrocyclization. Con rotatory electrocyclization means where the, okay, so we'll rotate this bond. Okay, we'll rotate this bond on same direction here. Okay, so on this side. Okay, bond in the sense the orbitals, isn't it? The orbitals, the yes, p orbital here, right? So this pi bond, you see. Okay, so you can draw the orbital picture here. For the easy understanding, you can draw the orbital picture. Okay, now here for the facilitating the bonding, right? For the facilitating the bonding, you have to rotate this p orbital, right? This is p orbital. This is also p orbital here, right? So here for the ring closure, okay, ring closure, you rotate this orbital either clockwise direction here or anti-clockwise direction. Okay, if you rotate this bond, okay, clockwise direction, right? If you rotate clockwise direction, then it becomes, okay, okay. So for example, if you rotate this clockwise direction and this one here like this, then what will happen here, right? So you will get this orientation, right? Now this p orbital end-to-end overlapping, right? End-to-end overlapping will be takes place, and it is going to form the sigma bond. Okay, if you rotate anti-clockwise direction here, then in that case also these two p orbitals comes closer, and the end orbital lobes will be, okay, overlap, and it forms a sigma bond here. Okay, so you can rotate either clockwise or the anti-clockwise, but both orbitals should be on same direction. For example, if you rotate this, right, if you rotate this orbital clockwise direction, this also rotated in the clockwise direction only. Okay, or if you rotate in the anti-clockwise direction, this is also rotated in the anti-clockwise direction, right? One clockwise and one anti-clockwise direction will not be allowed. So both should be in the same direction. So that is called the con rotation, right? Con rotation means rotation of the orbital in the clockwise or the anti-clockwise direction, on the same direction here, right? So that is con rotation here. This is ring closer, and in the ring opening, okay, so in the ring opening you can do this like this. Right. Next up, okay, so the disk rotation. Okay, so here the disk rotation means one is clockwise direction, another is anti-clockwise direction. Okay, this means the different right, the different type of rotation is takes place, right? Here the con means same, means the rotation of the orbital on same direction here, right? Either clockwise or the anti-clockwise. This is con rotation, and this means, okay, right? So this means the opposite direction. This is clockwise and this is anti-clockwise. This is plus, this is minus. Here is a either plus or minus and minus, right? Here plus and minus. This is this rotation or the con rotation here. Two types of rotations are possible, right? By this we will means do the electrocyclization, and we will get the products here, right? So in this particular example, you can see, right, the cis, cis 2, 4 hexadiene. Okay, so here this particular compound, it is going to form this cis 3, 3 dimethyl cyclobutene. This product is obtained here. Okay, now upon the rotation of these groups, right? So for example, if you do the dis rotation, right? If you do the dis rotation here, so we are getting, for example, if you do a rotation like this here, okay, you rotate like this and you rotate like this, right? Then what you get here, this methyl, right? So this methyl comes here and hydrogen comes here. Here also same thing. So we are getting this, right? So this product. So the stereochemistry of this product is a cis. Okay, cis 3, 4 dimethyl cyclobutene. Or another mode of the rotation here, right? So you rotate like this, means where the methyl comes down, right? The methyl, this methyl comes down, and this hydrogen goes up, right? And here also you do like this. So here in both cases it is this rotation, means the different opposite direction rotation only. But here where the this methyl is, right, rotated upward, and this methyl is this hydrogen is rotated downwards here. But in this case where this methyl is rotated downwards and hydrogen is rotated upwards here, then the product is trans here, right? Because here you see both are in the right. Okay, you see, yeah, this hydrogen and this hydrogen in the opposite direction, so it is trans. And here you see this hydrogen and this hydrogen in the same direction, so it is cis here. Okay, so the product obtained is depending on the rotation of the orbitals here, right? So you can take cis, trans 2, 4, 6 octane, right, in this compound, right? So upon ring, okay, so upon ring closure, right? So ring closure or the ring opening is takes place by rotation of these orbitals. The end, okay, the end terminal orbitals. You have to rotate the end terminal orbitals only, not the middle one, right? So when you rotate the end terminal orbitals here, either clockwise or the anti-clockwise, means con rotation or the disrotation here. Okay, so for example, by taking this cyclic compound cis 5 comma 5 5 comma 6 dimethyl 1 comma 3 cyclohexadiene, right? So when you do the con rotation, con means same, right, same side of the orientation, means the same direction, the rotation on the same direction here. Okay, either clockwise or the anti-clockwise. Okay, so when you rotate this compound, right, on this particular con rotation here, okay, so you see the opening like this. Okay, so where we are getting this product, and if you apply the, right, if you do the this rotation here, right, upon con rotation we are getting cis comma cis trans 246 octane, and upon this rotation we are getting trans comma cis comma trans 2 comma 46 octatriene. Okay, so here here in both cases we are getting the octatriene, here not octane, it is octatriene. Okay, so this is octatriene. Okay, so in both cases we are getting octatriene, but the stereochemistry is different. In this particular con rotation we are getting cis comma cis and trans here, and in the dis rotation we are getting trans comma cis comma trans. So the stereochemistry is different. Okay, so the stereochemistry is obtained depending on the way of the rotation, the mode of the rotation, either con rotation or the dis rotation here. Okay, now the cycloadditions. So in the electrocyclization we will apply the con rotation or the dis rotation, right? Con rotation means the rotation of the both end terminal orbitals on same direction, and dis rotation means the both end terminal orbitals on the opposite direction. And now cycloaddition reactions, right? The stereochemistry of the cycloaddition reaction. So in the cycloaddition reactions, the addition takes place, right? Addition takes place either by suprafacial or the anterofacial addition here. Okay, so suprafacial addition. What is suprafacial addition here? So suprafacial addition means the addition of the orbital from, right, same direction, right, same direction here, like your con rotation here also same direction here, right? So here for example, either top face or bottom face. Okay, top face and bottom face, right? So top phase addition or the bottom phase addition is takes place. So this is called the suprafacial addition, right? And the anterofacial addition. Anterofacial means where the addition of one orbital from the top face and addition of the another orbital from the bottom face, right? The opposite. So one orbital. Okay, so in the partner here you see, for example, here diene, right? Yeah, the olefin and olefin is going to adding. So here yeah, right? So in the suprafacial addition, where these two, right? Yeah, that, right? So these two, right? These two addition. Okay. So here this is top phase, this is top phase, this is bottom phase, this is bottom phase, and in this second partner This is top phase, this is top phase, this is bottom phase, this is bottom phase. So in the suprafacial addition, this is top phase and top phase addition is takes place. Okay. And this top phase and this top phase addition is takes place. And this bottom phase and this bottom phase, this bottom phase and bottom phase addition is takes place. This is suprafacial. And in the anterofacial, right? In the anterofacial here, so this is top phase here, top phase combined with the bottom phase here, right? And this, okay, this bottom phase combines with the top phase, whatever, right? So this kind of the opposite phase addition is takes place in the anterofacial, right? So suprafacial, the both means the both phases are same, either top phase addition or the bottom phase addition. In the antera, the opposite phase addition is takes place here. Okay. Yeah, in the suprafacial. Okay. So here one example is there. Right. So all these are the examples under this supra and antara here. Okay. Okay. Next, the molecular orbital theory here. Right? Here the molecular orbitals of conjugated polyenes. So this is very, very important in the exam point of view. So generally in the molecular orbital, right? The combination of the molecular orbital here, the drawing of the molecular orbital, right? So this is very important. So how to draw the molecular orbital and the number of nodes, right? And the symmetry properties in the examination. So they will ask that draw the molecular orbital of the particular polyene and designate its number of nodes and number of symmetry properties here. Okay. So first we'll see with this 1,3 butadiene. Okay. So 1,3 butadiene. Yeah, right. So here the 1,3 butadiene. So how many pi electrons are there? There are 4 pi electrons are there, right? So the number of pi electrons is equal to the number of orbitals here, right? The number of pi electrons is equal to the number of molecular orbitals. Okay. So first what you do here, just draw a line here and you draw 4, okay, pi molecular orbital diagrams here, right? So because there are 4 pi electrons are there, so 4 pi molecular orbitals are possible. Okay. And when you assign the nodes here, right? So for example here, right? Okay. So just you draw one line here and there are 4 pi electrons, right? So 1, 2, 3, 4, right? So 4. These 4, right? So 4 pi molecular orbitals here, right? Now, when you assign the nodes, right? When you assign the nodes, so first node you come from the bottom. Okay, so here all are okay. So node means when. So for example, here. Okay, here this orbital, right? So this orbital here, if it is right, so the both lobes are same, right? Then there is no node here, right? Zero, no node here. If it is opposite, right? Here this lobe is filled, this is unfilled. Then right, so this is this is unfilled here. Then this node. Okay, node is possible here. So this is one node. So like that, you can assign the right nodes here. So in this particular example, you see here, this is filled orbitals here, right? Filled lobes here, and the above one all are filled, and below one all are unfilled. Okay, so there is no node. Yeah, the zero number of nodes here. Okay, and here, okay, so these two are filled up, right? So the upper lobes are filled, and in this side the lower lobes are filled here. Okay, now you see here there is no node because here this is filled, so no node here, and here also no node, and here you see the upper lobe is filled, the lower lobe is this upper lobe is filled, this upper lobe is unfilled, so one node is possible, so one node. So like that. Okay, for pi 3 for the okay, so right, so now when you give this psi 3, when you draw this psi 3 orbital diagram, right? So here one above, one below. Okay, next here also same thing. Now you see right here, you see this is one lobe here. Okay, one node, and here is a one node. There are two nodes. Okay, so to calculate the number of nodes here, okay, the designation of the orbital -1, right? For example, psi 4 is there. Okay, psi 4 is there. So the number of nodes equal to psi 4 minus 1, that is equal to 3. Okay, if psi 3 is there, right, that equal number of nodes equal to psi 3 minus 1, that equal to 2. Right? So like that, you have to find out the number of nodes here, right? And you see, okay, here symmetry properties here, right? So plane of symmetry and C2 center of symmetry here. Okay, S means symmetric, A means asymmetric here, right? So where here in this particular compound, right, the psi4 molecular orbital, right? So there are plane of symmetry, right, is opposite, and the C2 symmetry, rotational axis of symmetry, right? M means the plane of symmetry, C2 means rotational axis of symmetry. Okay, so C2 symmetry is present and plane of symmetry is opposite here. So like that. For example, if M is present, right, so automatically C2 is absent here. So like that, we have to give the symmetry properties for this compound, right? Now we'll go with the one more example here, where 1, 3, 5. Right? So in this particular hexatriene, how many pi bonds are there? There are 3 pi bonds. Pi bonds means 6 pi electrons. So 6 molecular orbitals are possible. 6 molecular orbitals are possible here. Okay. The number of nodes here. When you give the number of nodes, simply just psi, okay, psi n minus 1. For example, psi n equal to 6 here, minus 1, that equal to 5. Okay, so there are 5 nodes are there. For example, psi 5 minus 1, that equal to 4. So 4 nodes are there. According to this number of nodes, you have to draw the molecular orbitals, right? So for example, psi 4 is there. Psi 4, that equal to 4 minus 1, that equal 3. So 3 nodes you have to assign. Okay, so how to draw the 3 nodes? Okay. Okay, 1, 2, 3, 4, 5, 6. Okay, so 3 nodes we have to assign. So for example, here, right? Right, so here 1 node and right here you see this is 1 node here, and here is 1 node, because you see here is unfilled, this is filled here, and here also this is unfilled, this is filled. So there are 3 nodes. So like that, you have to assign the number of nodes for this particular molecular orbitals, right? And with the odd electron means free radicals, right? For the free radicals and for the carbocations and for the carbanions also, you can draw the molecular orbitals here, right? So here you see with means the pi conjugated system with the odd number of p orbitals here, right? So for this, how to design right, how to draw the molecular orbital. For example, you take this particular, okay, so you take any carbocation or the carbanion or the free radical here. So allyl carbocation, for example, right? For allyl carbocation, so how many pi electrons are there? There are only 2 pi electron, and here the positive charge is there. So positive charge, okay, you can draw like this here. And if it is free radical, okay, if it is free radical, so you can consider that free radical as a p orbital here. So the number of electrons is 3, because here the 2 pi electrons and 1 free radical. This is also considered as a free radical, also considered as a pi electron here. So total 3 pi electrons are there. So you can draw the 3 molecular orbitals for this particular allyl radical here. Okay, and next, what is that for 2,4 pentadiene systems here. So for this also, for carbanion, carbocation, you can draw the particular molecular orbitals here. Okay, and here the carbocation, and I will go with this 2,4 pentadienyl free radical here. Right. So here in this pentadienyl free radical, how many pi electrons are there? Here is a 2 pi bonds, so it is 4. Okay, so 2 pi bonds, it is 4 pi electrons here, and the free radical is there. Right. So total there are 5 pi electrons are there. So you can give this particular 5 electron in the order, right? So psi1, psi2, psi3, psi4, psi5. There are 5 molecular orbitals are possible here. Okay? There are 5 p electrons here. So upon excitation, right? Upon excitation, one of the electron is going to promote it from lower energy level here. Okay. So in the excitation here, one of the electron is going to promote it here. And how to draw this particular molecular orbital here? So you can see, for example, right? So in this, what is it? 2, 4, 6 penta triennial system, right? So here there are 6 pi electrons are there. Okay, so 6 pi electrons. You can draw this 6 pi orbitals here, and where this is one of the carbon is carrying the positive charge, right? So you will right. So where you can keep this particular, because it is node here. Okay, means it is nodal center. Okay. Next, the electrocyclization reactions. But so how to draw the, so how to means study this particular electrocyclization reaction with help of the PMO method. PMO means the perturbational molecular orbital method here. So in this particular PMO method, right? So generally we'll identify whether it is right, aromatic or the non-aromatic molecule. Right? So aromatic here the means there are two
లవంగాలు ఏరే ఉన్నాయా ఇంకా లవంగాలు అది కొంచెం మిగతా అన్నీ అలా ధనియాలు వేసి పట్టి
okay. So in the PMO method, so means here there are two transition states are possible here. One is the Hackett transition state, another is a Mobius transition state, right? So Hackett transition state is nothing but here when you take the molecular orbital diagram, right? So if it is having the 0 or even number of nodes, means where we are not finding the electron is a node.
మనం బెల్లంకాయలు ఉంటాయి అవి కూడా పట్టుకొచ్చినారు ఏర్పాటు చేస్తారు కదా ముక్క ఉంటాయి.
So here this is the node. Okay, this is node. Right? So this is node point here, nodal point. Node means where the finding of electron is 0. Right? Finding of electron is 0 is called the node here. Okay. So here the 0 number of nodes or the even number of nodes are there. Right? Then it is Haeckel transition state. If odd number of nodes are found, then it is transition state. Right? So you can decide the aromaticity by this particular PMO method, perturbational molecular orbital. Yes. Here. Yes. In the Haeckel transition state, right? So means the Haeckel transition state is with 0 or even number of nodes. Okay. And you see where this transition state, right? With there are two systems are there, right? In both cases, in both Haeckel transition state and Mobius transition state, there are two systems are involved, like 4n plus 2 pi electron system and 4 pi electron system here, right? 4n plus 2 pi electron system, 4n pi electron system. Okay, and for in the 4n plus 2 pi electron system here is there, then Haeckel aromatic transition state here. Right, 4 pi electron system is there, then it is Haeckel anti-aromatic transition state. Two kinds of transition states are possible here, and in the Mobius also same. But the only thing is where this Mobius transition state is assigned for the molecular orbital having odd number of nodes here, right? Which is having the odd number of nodes, and in that case also it is reverse. Okay, transition state. If the pi electron system is 4n plus 2, so it is Haeckel aromatic transition state. But in the Mobius, it is reverse. If it is 4n plus 2, it is Mobius anti-aromatic transition state. Okay, and in the Haeckel transition state, if that particular system is 4n pi electron system, so it is Haeckel anti-aromatic transition state. And if it is 4n plus 2, it is Mobius anti-aromatic system. If it is 4n system, it is Mobius aromatic transition state. Right? To find out that it is Mobius transition state or the Haeckel transition state. Okay. So in this particular example where 1,3 butadiene, 1,3 butadiene, you see. So this in this particular, right, in this particular molecular orbital diagram. Okay. Right. So in this particular molecular orbital diagram here, right? So where we are taking. Right? So you take any molecular orbital diagram here, right? We are taking this. Now what we are doing? So in the so in this particular ring closure, right? Either ring closure or the ring opening, whatever. So in the ring closure, for example, if you are doing the con rotation, right? If you are doing the con rotation here, okay, con rotation. So con rotation means same direction of rotation here. For example, we are rotating this bond towards, right, anti-clockwise. This is also anti-clockwise here. Then what happens here? You see, this slope is right. So this slope is comes here. Okay, so you will get this kind of orientation, right? So this kind of orientation here, and here when you do the con rotation to this side here, again you will get this orientation. And what is happening here? Right? So you will get the node because here this is empty and this is filled here. So node is generated. Then how many nodes are there? One node here. So odd number of nodes. Odd number of nodes means it is Mobius aromatic system. Right? Mobius aromatic system. And in the Mobius, there is how many electrons are there? It is 4n electron system. Right? So 4n electron system, what is that? 4n electron system. It means it is Mobius aromatic transition state. Mobius aromatic transition. Okay. So if you rotate the, right, if you rotate the means opposite direction, means if you do the perform the disrotation to this same system, okay, if you rotate this rotation, there is a con rotation, right, where we are doing the con rotation where the on same side direction here. So then you see this comes here, this comes here. So where the node is formed and this node is zero node here, sorry, one node, right? One node is there. One node means odd number of nodes. Okay, odd number of nodes means it is Mobius system. Okay, Mobius transition. In the Mobius transition system, it is 4n pi system, 4n pi electron system. Mobius aromatic. Okay, Mobius aromatic transition state. Okay, and for example, if you are not doing rotation, if you do the this rotation to this system here. This rotation means this is direction. So this is clockwise direction rotation. This is clockwise direction here. Then what happens here? So where you will get like this. So this one. No node is there, right? So because no bonding is possible here. Okay. So this is filled and this is also filled here. So zero node. Okay, zero node. So zero node means it is zero or odd number of nodes. Okay, then it is comes under Huckel aromatic transition state. Right? Right. So if zero or odd number of nodes here. Okay. So zero here you see. There are zero or sorry, even number of nodes, it is Huckel transition state. Odd number of nodes, it is Mobius transition state here. Right. So when you do the right, when you do the this rotation, right? So this rotation to this foreign system here, right? So where you will find the zero nodes here, and in the nodes it is Huckel anti-aromatic system, right? If it is Huckel anti-aromatic system, so it is Mobius aromatic transition state, right? So like that you can see here. Okay, in the con rotation also you see, and the dis rotation, same thing, where we are not finding any node. Okay, zero number of nodes. So it is Huckel anti-aromatic transition state here. And next, for this 4n plus 2 pi electronic system, right? So 4n plus 2 pi electronic system here, where the 6 pi electrons are there. 6 pi electron means it is 4n plus 2. It comes under 4n plus 2 system here. Okay, now you see in this particular example, right? So here you take the molecular orbital here. Okay, so where we are doing the con rotation, right? So okay, so we are doing this con rotation. Con rotation means same side direction, same side orientation, means the rotation here, right? So then what happens here when you rotate this molecular orbital on the same direction, right? So then you see this you can observe like this here, right? So this comes here. Okay, when you rotate this, so this lobe comes this side and the unfilled lobe comes this side here, and this is also rotated on clockwise direction. So then you see you will get like this here, right? So what happens here? So yeah, the filled one, it is unfilled, so one lobe is observed, sorry, one node is observed here. One node means odd number of node. Okay, odd node means it is comes under the Mobius system, and Mobius 4n plus 2, right? 4n plus 2 pi electron system is Mobius anti-aromatic transition state, right? Mobius anti-aromatic transition state. And next, when you are doing the dis rotation to this system, right? So then what will happen? You can see if you perform the dis rotation. Right? So when you do the dis rotation to this one here, so dis rotation means the opposite direction rotational. Okay, so when you rotate this molecular orbital towards clockwise direction, and this is anti-clockwise here. Okay, now when you rotate this molecular orbital clockwise direction, so this comes here, right? like this. And when you rotate this molecular orbital anti-clockwise here, then you will get this one, right? Then what happens here? So no bonding is possible. No bonding is possible here. Means here there is no node. Okay, zero number of node. Zero number of node. Zero number of node means no bonding is possible here. Okay, so it is comes under Huckel aromatic, Huckel transition state, right? Huckel transition state, and it is 4n plus 2 pi system. So Huckel aromatic transition state. Okay, so like that, how to find out whether it is Huckel system or the Mobius system. And in the Huckel system, whether it is 4n plus system or the 4n system, and it is Huckel aromatic system or the Huckel anti-aromatic system here. Okay, so the selection rule for this PMO theory, you can see this in this table here. Okay, right. So the complete right, the PMO theory, right, the selection rules are here. If it is 4n system, number of right, electrons in the transition state, if it is 4n system, so when you perform the Kohn rotation here, right, so generally we'll get the odd number of nodes here. Then it is odd number of nodes, then it is aromatic. Okay, and the conditions which are allowed here is a delta. Delta means thermally allowed and photochemically forbidden here, right? The reaction conditions. And for this disrotation, generally we'll get the zero or even number of nodes here for this disrotation for 4n system here, right? The zero or even number of nodes are observed, and the aromaticity transition state is anti-aromatic. Okay, anti-aromatic, and the reaction conditions which are favored is where the photochemically it is favored, or the photochemically allowed and thermally forbidden here. Okay, next 4n plus 2 system where the number of nodes is odd and the aromatic state is anti-aromatic here, and reaction conditions are photochemically allowed and thermally forbidden. And 4n plus 2 system, this rotation, where you will get the zero or even number of nodes here, and aromatic nature is the aromatic. The reaction conditions which are favored is photochemically forbidden and thermally allowed here. Okay, so this is the right. So this is your Pericyclic reaction. I'm stopping here.